Talking about ATP production, just to go back and review where we are. We store a small amount of ATP in our cells, and that ATP is used to do work, and it's gone very quickly when we're doing any amount of work. So as soon as our stored ATP is gone, we have to phosphorylate an ADP, and we need some energy to do that and create new ATP, which we can then use to do work. So in this chapter, what we're talking about is how the body goes about making ATP. And we said that there are anaerobic systems and aerobic systems. We talked about ATP-PCR. We said that that is the immediate system. It's the first one to kick in to replace ATP. And it's the fastest, but it also fatigues it's fastest in its rate of ATP production, but it also fatigues the fastest. The second system to kick in is the glycolytic system or glycolysis. Again, a very fast system, not as fast as ATP PCR production of ATP, but still relatively fast, but again, not fatigue resistant. More fatigue resistant than ATP PCR, but not as much as the aerobic systems. And that's where we're at now with the aerobic systems, which are also called the oxidative systems. And there are three systems that we're going to talk about. In this recording, we're going to focus on Krebs cycle. Later on, we'll talk about beta oxidation, which uses fat. And then we will talk about electron transport chain. So remember that at the end of glycolysis, okay, we started with glucose 6-phosphate. At the end of glycolysis, we ended up with 2 pyruvate molecules. Those pyruvates can do one of two things. They can become lactic acid, or they can cross over into the mitochondria and go on to the aerobic systems. Okay, and that's what we're going to focus on here, is the pyruvate that goes into the mitochondria. Okay, so these are the oxidative systems: Krebs cycle, beta oxidation, electron transport. They are long-term energy systems, which means that they are fatigue resistant. Okay, they can produce ATP for a long period of time before they fatigue, but they produce ATP at a slower rate than the anaerobic systems, which are not fatigue resistant. The oxidative systems go on within the mitochondria of our cells. Remember, the anaerobic systems are in the cytoplasm. The function of the oxidative systems is to make ATP either from glucose or from fat. Okay. So remember that with glycolysis, we started with glucose 6-phosphate. We end up with 2 pyruvates. Okay, and if those go into the mitochondria, okay, they go into the oxidative systems. So we can now make ATP from pyruvate, which originated as glucose. So sometimes we say that we are making ATP from the further breakdown of glucose. Okay, so we're making ATP from glucose, but we're actually making ATP from pyruvate, which originated as glucose. And when we talk about beta oxidation, you'll see how the oxidative systems make ATP using fat. So here we have the Krebs cycle, and as with glycolysis, I'm going to eliminate some of the details here so we can focus in on what's most important for now. So everything in these green boxes, these are all substrates. It's not important right now to know all of their names. And then between each chemical reaction we have enzymes. Okay, but again, it's not important right now to know all of these enzyme names, but it is important to know that there are enzymes. Okay. We're not going to worry about water right now. We're not going to worry about CoA right now. We're not going to talk about GTP and GDP. Okay, just want you to focus in on the ATP. Let's not worry about water. Okay, and then there's some mistakes here. For one, there is no CO2 here. That was actually supposed to say CoA, but we're not going to worry about the CoAs. Anytime you see an NADH, you should also have an H+. So let's add those back in. Okay, and this FADH2 is okay because it has the 2 hydrogens. All right, so let's go through the steps. So remember that we originated from the cytoplasm. We are now in the mitochondria. Okay, and this pyruvate came from glycolysis. And remember that when we started with glucose 6-phosphate, at the end, we have 2 pyruvates. Okay, but what we're going to do is we're going to trace 1 pyruvate at a time. But keep in mind, and I'll come back to this, that there are 2 pyruvates that result from glucose 6-phosphate. So everything occurs twice, okay, because everything that happens to 1 pyruvate happens to the second pyruvate. So everything you see here is going to happen twice if we originated with glucose. So keep that in mind. So the first step here, this is called the intermediate step. And in the intermediate step, pyruvate, the substrate pyruvate, becomes acetyl-CoA. In the process, we produce a CO2, and we end up with something called NADH plus H+. Okay. That CO2 is then going to go to your lungs, so we can get rid of it, exhale it. And the NAD plus H plus is going to go off to the electron transport chain and give us some ATP. We'll talk about that in another recording. Okay. So basically, going into this reaction, we had a pyruvate, we had an NAD. Coming out of the reaction, we have a CO2, an acetyl-CoA, and an NADH plus H plus. Acetyl-CoA then goes into the Krebs cycle. CO2 goes to the lungs, and the NADH plus H goes to the electron transport chain and gives us more ATP. Okay. So now we have acetyl-CoA, and in the first step of Krebs cycle, oxaloacetate substrate combines with the acetyl-CoA substrate and forms a new substrate called citrate. Okay, so that's the first step of the Krebs cycle. And then we go through a cycle where each substrate is becoming another substrate, okay, as a result of chemical reactions. So keep in mind that there's multiple chemical reactions going on. But what I want to focus on now is what else is going on. Okay, as these chemical reactions are going on, what else is going on? Okay. So we see that we produce CO2. That's going to go off to the lungs. We produce another CO2, which will also go off to the lungs. So we produce 2 CO2s. We end up with NADH, 1, 2, 3 of those. So we have 3 NADH plus H plus. We also end up with an FADH2, 1 FADH2. Okay, and remember each of these go off to electron transport. FADH2 also goes off to electron transport. And then the last thing here is we get an ATP. Okay, so we've sent one pyruvate molecule through the intermediate step. We ended up with acetyl-CoA. In the intermediate step, we get 1 NADH plus H plus, which goes to electron transport. We get 1 CO2, which goes to the lungs. Now we go into the Krebs cycle. The oxaloacetate combines with acetyl-CoA, forming citrate, which starts the cycle. Within this cycle, we end up with 1 ATP, which was here, 2 CO2s, 3 NADH plus H plus, 1 FADH2. Okay. The NADHs and FADH2s go to electron transport. The CO2s go off to the lungs so we can exhale and get rid of them. The ATP is used to do work. Okay. And so you can see that at the end of this cycle, we end up with oxaloacetate, which then combines with another acetyl-CoA, and that's what continues this cycle going. Okay, so as long as the cycle occurs, creates oxaloacetate, glycolysis is occurring, producing pyruvate, we can get acetyl-CoA. Okay, so as long as we have acetyl-CoA, we can combine that with oxaloacetate, make citrate, and then the cycle continues. Okay. Now, let's go back for a minute. I want to remind you that what we just did was we traced one cycle, one intermediate step, one Krebs cycle. But if we started with a glucose molecule, we ended up with 2 pyruvates, which means everything we just talked about happens twice. Okay. So, 2 things important here. First of all, you need to understand what happens in one intermediate step, what happens in one Krebs cycle, and then the next thing you need to know is how many times do we go through those. Okay. So if we start with glucose, we have 2 pyruvates, so we have 2 intermediate steps. We're going to have 2 acetyl-CoAs as a result, so we're going to go through Krebs cycle twice. Okay. This is not the same as fat. Okay. When we start from fat, we don't go through the intermediate step, and we go through the Krebs cycle more than twice. Okay, so don't worry about that now. We're going to talk about that on another recording. But I just want you to know these steps, know what happens in one, and then the next step is to know how many times does this step occur, and that's going to be based on what you started with. So I will tell you, if we start with a glucose molecule, how many Krebs cycles do we go through? And what do we end up with as a result of those Krebs cycles? So that's a way to think about it. So aerobic ATP production occurs in 3 steps. Okay, the first step is to generate an acetyl-CoA. okay, which if we start from glucose, we go through glycolysis, we get 2 pyruvates. Those pyruvates go into the intermediate step, and out come 2 acetyl-CoAs. Okay? And those go into Krebs cycle. If we start with fat, we go through a process called beta oxidation. Beta oxidation creates acetyl-CoA. For fat, the same way the intermediate step, or in a similar way that the intermediate step created acetyl-CoA from glucose, from what originated as glucose. But we'll talk about beta oxidation later. Okay. Every acetyl-CoA feeds into the Krebs cycle by combining with oxaloacetate, producing citrate. Okay. And then as we go through the Krebs cycle, we produce 3 NADH plus H plus 1 FADH2, and those go on to the electron transport chain. We also produce 2 CO2, which are exhaled through the lungs, and 1 ATP. Okay? So for 1 acetyl-CoA, this is what we get. Okay? But if we originated from glucose, we have 2 pyruvates, therefore we have 2 acetyl-CoAs, therefore we go through the Krebs cycle twice, therefore everything in this box is type 2. This will be 6, this will be 2, this will be 4, and this will be 2. Okay. So this is a summary of what we've already talked about. So here we have the cytosol, same as cytoplasm. So what we have here is glycolysis. If we start with, we're always going to start with glucose 6-phosphate. In this example, we're starting with blood glucose. Horrible. Blood glucose, okay. Glucose 6-phosphate goes through glycolysis. Along the way, we invest 2 ATP. We produce 4. Okay, go back to your glycolysis slide to review this. So we end up with a net gain of 2. We've also produced 2 NADH plus H's, which go to the electron transport chain, which is also in the mitochondria. At the end of glycolysis, we have 2 pyruvates. Okay. Those pyruvates can become lactic acid, or they can go into the mitochondria. Let's trace it. Let's assume that they all go into the mitochondria. What happens next is called the intermediate step, where pyruvate becomes acetyl-CoA. And we have 2 pyruvates because we started with glucose, so we end up with 2 acetyl-CoAs. So everything is double. So in the intermediate step, we produce 2 NADH plus H's, 1 per intermediate step, times 2 is 2, which goes to electron transport. We also produce CO2, 1 CO2 for each intermediate step, but we have 2 of them. Those CO2s go off to the lungs, so we can exhale them. And at the end of the intermediate step, we're left with acetyl-CoA, which can now enter Krebs cycle. So acetyl-CoA binds with oxaloacetate, gives us citrate, and now we go through the Krebs cycle. Okay. In the process of the Krebs cycle, okay, and here we're talking about 2 of them, because we have 2 acetyl-CoAs, we get 6 NADH plus H, which go to electron transport. Okay, so we get 3 for each cycle, times 2 cycles is 6. We get 2 FADH2s, which go to the electron transport chain. Again, we get 1 FADH2 per cycle. but we go through the cycle twice because we have 2 acetyl-CoAs. We get 2 ATPs, okay, 1 per cycle times 2 cycles is 2. Don't worry about the water. We get 4 CO2s total that go to the lungs so we can exhale. We get 2 CO2s for each Krebs cycle times 2 Krebs cycles is 4. Later on, which we'll talk about next, we get the electron transport chain. And you can see going into the electron transport chain, we have some oxygen, we produce some water, and we produce a good chunk of ATP. But we will talk about that next. But this is a nice summary slide.